Hello everyone, this is Professor S. M. Orkhade. In today's lecture, we are going to learn the golden section method from 5th unit of optimization techniques. All of we know the Fibonacci series which contains the numbers 1, 1, 2, 3, 5 and so on. That means we can represent any Fibonacci number fn as fn is equal to fn minus 1 plus fn minus 2. If we divide both the sides of this expression by fn minus 1, then we'll get the equation number 1, and from this equation number 1, the term fn by fn minus 1 is called as a golden ratio, which is represented by gamma. If we further simplify this equation 1, we'll get a quadratic equation in terms of gamma. Again, if we find the root, we'll get gamma is equal to 1.618 or minus 1.618. Minus 1.618 is nothing but the conjugate root or conjugate golden ratio. But we will select 1.618 as the value of the golden ratio because it is the ratio of the two Fibonacci numbers. So we will be selecting the real root, that is gamma is equal to 1.618. Now this table shows in this table the golden ratio is calculated for the consecutive pairs of the Fibonacci numbers. If you observe here, for the first 4 to 5 terms, the golden ratio is coming out to be approximately equal. But if we move further in the Fibonacci series, then the ratio of the two numbers, that means any Fibonacci number divided by its previous number, is coming out to be exactly equal to 0.618. So this is the table which shows the relation in between the Fibonacci series and a golden ratio. Golden ratio is also having number of applications or interesting facts behind it. It is having a historical background. If we see the ancient buildings or structures like pyramids, even the Taj Mahal also follows the golden ratio. If we implement a golden ratio in the design of any object or any structure, then the appearance of that thing will be a pleasant one, or it will be having a nice look. Golden ratio is having the use even in the painting, drawing and music also. People use this ratio in selecting the size of postcard, in selecting the size of the iPhones or widescreen TVs, and it is also used in selecting the size of a room, and it is widely used in the civil structures and many more things. Now consider a room which is having a size as given below, that is A by B. A is the longer length and B is the width. Okay. Now if A plus B divided by A is equal to A by B, and if this expression is equated to gamma, then we can conclude that the appearance of the room will be a nice one. The next is the similar example. If we are having suppose a line segment, and if we divide that line segment into two parts, one is the longer part and the next one is a smaller one. Let us take the length of the longer part as A and the length of the smaller part be B. Then A by B equal to A plus B divided by A should be equal to 1.618. So this is the criteria for applying golden ratio. Now let us come on to the golden section method. This method uses the golden ratio, and this method is very similar to the Fibonacci search method, but in golden section method we get one relaxation, that the number of experiments are not predefined. We have to select the number of experiments in the process itself, and we can perform a large number of experiments also to get the better approximation. And yes, obviously it is an iterative process. The necessary condition for applying this golden section method is the function must be unimodal in the given interval of uncertainty. If suppose the function is a multimodal, that means if the function is having number of minima maxima, then what we'll have to do, we'll have to break the given interval into number of subintervals, and for those subintervals we'll have to apply the golden section method to find out the local minima or local maxima, and from those obtained local values we will have to find out finally the global value or global optimal value. Now we will go through the working rule for this golden section method. Let us consider the given interval of uncertainty is L0 is equal to A to B. This is the initial interval. I have drawn it. I have drawn the interval here from A to B. The function is considered here, which is shown by red color. After drawing the interval from A to B, we have located 2 points x1 and x2 such that both are L2 star away from extreme ends. Then we can again observe here one thing, that the minimum of the function is lying somewhere near to point x1. In the next step, we have to calculate the value of L2 star. L2 star is equal to limit n tends to infinity fn minus 2 by fn into L0. If we are able to remember, this formula is just same as that of the Fibonacci series, Fibonacci search method. L2 star is equal to fn minus 2 by fn into L0. This expression we know. Again, in this case, we have further simplified it. We can write fn minus 2 by fn as fn minus 2 by fn minus 1 into fn minus 1 upon fn. So, both these terms are equal to 1 upon gamma. That means, finally, if we simplify this, we will get L2 star is equal to 1 upon gamma square into L0. After calculating the value of L2 star, we can easily calculate the value of x1 and x2. x1 will be equal to a plus L2 star and x2 will be equal to b minus L2 star. Now, after calculating the values of x1 and x2, we have to calculate the value of the functions f of x1 and f of x2, and then we will have to check whether f of x1 is less than or greater than f of x2. Here f of x1 is less than f of x2. If the problem is of minimization, then we will have to discard x2 comma b, and if the problem is of maximization, then we will have to discard a comma x1. Thus, length of the next interval will be either a comma x2 or x1 comma b. But here we will be considering the minimization case. Therefore, the new interval of uncertainty will be as shown below. That is from a to x2. And the length L2 will be calculated as limit n tends to infinity fn minus 1 upon fn into L0. This is again the formula which we have taken from the Fibonacci search method, and if we simplify this again, we will get L2 is equal to 1 upon gamma into L0. After calculating the length of the next interval, new interval, we will have to calculate the value of L3 star by locating the new point x3 into the given into the new interval, and again by calculating the L3 star, we are getting the L3 star value as 1 upon gamma cube into L0. Then again by calculating L3 star, we have to calculate the values of f of x1 and f of x3, and then again by checking the conditions greater than or less than, we can find out the length of the next interval. In this way we have to proceed, and finally we can write the general expressions for the jth experiment as Lj star is equal to 1 upon gamma raised to power j into L0, and Lj, that is the length of the new interval, is equal to 1 upon gamma raised to power j minus 1 into L0. So I will say that the procedure is just similar to the Fibonacci search method, and we have taken the same formulae as we have taken in the Fibonacci search method for calculating Lj star and Lj. Only certain modifications have been done for this golden section method. We have simplified it further. Now after this we are going to solve one example by using this golden section method. Let us move on to that. Before going to the example, you can just note down this point. After finding the jth experiment, find the length of the final interval. If the length of Lj is less than epsilon, then we will conclude that the interval of uncertainty is the final one for optimal solution, and by taking the half of that interval, we will get the optimal solution. Now we will solve the example which is minimize f of x equal to 4x cube plus x square minus 7x plus 14 within the interval 0 to 1 using golden section method. The stopping tolerance epsilon is given as 0.15. Here in the given example, the initial interval of uncertainty L0 is equal to 0 to 1. So just at start we have drawn directly the given interval from 0 to 1. Then we have located 2 points x1 and x2 such that x1 will be L2 star away from 0 and x2 will be L2 star away from 1. And we have calculated the value of L2 star by using the formula 1 upon gamma square into L0. So it is coming out to be 0.3819. After calculating L2 star, we have calculated the values of x1 and x2. Then calculated f of x1 and f of x2. Here in this case, f of x1 is greater than f of x2. Therefore, we can discard 0, x1, this much length of the interval. Therefore, the new interval of uncertainty will be x1, 1 and L2 can be calculated by using the formula 1 upon gamma into L0. Now in the next step we will have to calculate the value of L3 star by locating the new point x3 into the new interval. L3 star is equal to 0.2361 that we have calculated. Then we have to again calculate the value of x3 and f of x3. In this case, f of x2 is less than f of x3. Therefore, we can discard x3, 1. Thus, the new interval length will be x1, x3. The same I have drawn again, the same length have been drawn here. Then the similar steps we have to follow. We have calculated L4 star by locating the new point x4 into the new interval. Then again we have calculated x4, f of x4. Again we have found that we have got that f of x4 is greater than f of x2. Therefore, we have discarded x1, x4. And the next interval length will be L4 is equal to 0.2361. If you know the Fibonacci search method, then you can efficiently solve this example also. Again now L5 star x5 have been calculated. I am not going into the detail. You can just take a screenshot of this and solve it by yourself afterwards. Now at last step I am coming. L5 is equal to 0.1458. What was the value of the stopping tolerance epsilon given in the example? Epsilon is equal to 0.15 and we are getting that L5 is equal to 0.1458, which is less than the epsilon. Okay, this is the stopping tolerance. Therefore, the final interval of the uncertainty will be x2, x3 by discarding x4, x2 from the last interval. And we have calculated the length of the final interval. It is coming out to be L equal to 0.1459. So you can solve any example by using these steps for the golden section method. Thank you.